Today we're going to talk about the biology of excitement. I'll see you inside. So let's first take a brief moment to talk about what actually makes a neuron fire. A neuron is actually a cell in your brain that will release a neurotransmitter. And these neurotransmitters are just chemical signals that will basically influence your body to partake or not to partake in a specific behavior. Simply putting your mind and your physiology in a specific state that promotes or downregulates the likelihood that you will engage in something. And I think a great place to start is, what the heck does it actually mean when a neuron fires? Simply, when someone says that a neuron has fired, they mean that it has released a neurotransmitter that is stored inside of it. And a neurotransmitter is a chemical produced in the body that will actually bind to a receptor. And neurotransmitters are actually made inside of a neuron and are stored in what's called a vesicle. And a vesicle is like a big envelope full of neurotransmitters that sits inside of a neuron until the neuron is ready to release them. And the thing that makes a neuron release a neurotransmitter is called an action potential. And this action potential is actually when the neuron reaches a specific voltage. The voltage is simply the difference between the charge inside of a neuron and the charge outside a neuron. And at rest, or when a neuron really isn't doing anything, it's estimated that a neuron is to be about negative 70 millivolts. So if it is negative 70 millivolts, it means that the voltage inside the neuron is 70 millivolts lower than the voltage outside of the neuron. And now different neurons have different voltages that they need to meet, or different thresholds to meet their action potential. But once they do, the neurotransmitter will bind to the membrane of the neuron and release the neurotransmitter into what is referred to as the synapse. And now raising or lowering the voltage is simply just an ionic exchange of things like sodium, potassium, and calcium going in and out of the cell. And now I mentioned the synapse, and I want to come back to that. The synapse is simply the space between two neurons. And it is important to know that the neuron that actually contains the neurotransmitter is called the presynaptic neuron. And when the neuron releases a the neurotransmitter goes through the synapse, or the space between two neurons, and it will bind to a receptor on another neuron. And this neuron is called the postsynaptic neuron. And once it binds to the receptor, the neurotransmitter will just increase the likelihood of causing whatever behavior or brain state it is associated with. The best way that I have found for most people to think about this is that the presynaptic neuron is like the pitcher and the postsynaptic neuron is like the catcher. And once the neurotransmitter has docked into the receptor, it will sit there and continue to cause whatever function it is associated with. And then the receptor typically requires an enzyme to metabolize the neurotransmitter in order to remove it from the receptor. And now this is kind of how neurons fire, but I want to kind of come back to the action potential and talk about two neurotransmitters that either drastically increase or drastically decrease the likelihood that a neurotransmitter will fire. I apologize, I misspoke. The likelihood that a neuron will fire, releasing the neurotransmitter. So these two neurotransmitters that I'm going to talk about are actually only made up of one amino acid. These are glutamate and GABA. And now I hope to do an entirely separate episode on each one of these neurotransmitters, but today I'm going to try and break it down simply. Glutamate causes a cascade of events that make it far more likely for a neuron to reach its action potential and release the neurotransmitter that's stored inside. Simply, it will increase the amount of positive molecules inside the cell, which increases the voltage of the neuron. Therefore, it is much easier for the neuron to reach the action potential required for the vesicle to bind to the membrane and release the neurotransmitter. So if we do not have enough glutamate, we would likely have very low brain activity and neurotransmitter production. However, having extremely high glutamate would likely make it very difficult to relax and focus. You can think of the time when you might be sitting in bed and your brain can't turn off. This is because you likely have more glutamate than you would want to have right before going to sleep. With that being said, there are a multitude of other reasons that this would occur. One of them may actually be not having enough of the other neurotransmitter I'd like to discuss, which is GABA. GABA is actually referred to as the main inhibitory neurotransmitter, and it seems to do the exact opposite of glutamate. It allows positive ions to exit the cell, reducing the voltage inside of the neuron, and increasing the voltage outside of the neuron. Thus, the neuron is much less likely to reach its positive action potential. And I find GABA's role in psychological abnormalities to be extremely interesting because it seems to interplay with ADHD, because not having enough GABA makes it very difficult to focus. GABA will actually shut down different neurons and neural connections so that they are not continuously firing when they are not needed. If you do not have enough GABA, you cannot maintain your attention on the specific task you are trying to do because other neurons and neural connections are firing simultaneously. When someone is extremely focused on a singular task, even though they have high brain activity, it is likely that they have very high GABA as well because they are actively inhibiting other neurons from firing. Therefore, their attention remains on a singular thing because it is the only or one of the only neural connections that is being stimulated at the moment. So having low GABA, you are unable to do this, and your attention will constantly be being pulled in different directions. So I want to kind of backtrack a little bit and come back to glutamate and how this affects our senses. If we have high glutamate, we will likely have strong activity from our senses, such as touch, taste, and smell. Interestingly, MSG is oftentimes added to food. MSG is actually monosodium glutamate. And as the name might imply, monosodium glutamate has glutamate in it. And studies definitely demonstrate that when you add it to food, it increases its palate excitability and increases our likelihood of overeating. And I assure you that if you look on the back of the packages of many processed foods or foods that you find extremely rewarding, they will likely have monosodium glutamate included. And with that being said, I don't know if it's ever actually been tried, but it does kind of make me think and just ponder the idea of putting GABA inside of food to maybe decrease its palatability. But I don't know how exciting or tasty this food would actually be. With that being said, I think I'm going to leave this one here. Today I kind of just discussed the neurochemistry of brain activity, and hopefully you learned something and just enjoyed it, because honestly I enjoyed talking about it. I hope to see you next episode. I'm not sure what it'll be about yet, but we'll see what happens. You can follow me on all of my social media by just looking in the description of this podcast. And I want to just say thank you for listening, and I hope to see you next episode.